trillions of high energy charged particles enter Earth's atmosphere every second. Where do they come from? Deep outer space. They have energies far more than the fastest particle colliders on the planet. When they hit our atmosphere, the collision leads to a plethora of charged particles raining down as a cosmic shower. Here on Earth, we are safe. But these might be the most important things to worry about when humanity would go interstellar. This is about cosmic rays. Even though they are called rays, they're not really light rays. It's a common misnomer. Those were early days, we still didn't know what these things really were. As said, the byproduct of these cosmic ray collisions could travel to the surface of the planet. And it's actually simple enough to detect those. All you need is a cloud chamber. It may sound fancy, but if you just fill up a transparent container with supersaturated alcohol vapor, when a charged particle would move through this, the alcohol vapor would condense around the path of the particle, showing a trail of its motion. But in those early days, we still didn't know if they were coming from the sun or from within the earth. Turned out to be neither. In 1912, Victor Hess used the newly arrived hydrogen balloons to take the electroscope up in the atmosphere. Back in the day, the leading view was that these radiations are really coming from radiative processes happening within Earth. And so what Hess was trying to do was to show if that radiation drops to zero if it goes up above in the atmosphere far enough. What he saw was, nope, that didn't happen. It's actually the skies. The radiation increased several folds up in the atmosphere. So anybody would then think that it therefore must be sun that must be emitting those radiations. And so they took a flight during a solar eclipse. I would have suggested doing it overnight. Wouldn't it have worked the same? But solar eclipse works fine. What they found was that it didn't seem to have much of an effect at all. The sun doesn't seem to be a major contributor of this whatever radiation. Which means if it's not coming from the sun, and it's not coming from within Earth, these radiations must therefore be coming from deep outer space. Hence he named them, you guessed it, cosmic rays. Rays because they seem to travel in straight lines, people thought that these are highly energetic electromagnetic waves, similar to how cathode rays were called rays even though they were really electrons. Told you, common misnomer. So what are cosmic rays? About 90% of them is ionized hydrogen, i.e. protons. 9% is bare helium nuclei, also known as alpha rays or particles, if you know. The rest is everything from electrons, positrons, antiprotons, and bare nuclei of other heavier elements. Essentially charged particles. The core mystery isn't as much about their presence. There are mechanisms at play that could create them. A bigger wonder is the sheer amount and energies these particles reach. Some of the lower energy ones can be traced back to the sun itself. I know these are called cosmic rays, but well, the sun also shoots at us ionized particles. It's just a very tiny fraction of net cosmic ray flux. Roughly 1%. Obviously, the actual amount changes with sun's activity. There have been observations of solar flares being correlated with increased cosmic rays. And so the sun is most definitely a source. A smaller one though. Also, cosmic rays coming from the sun have lower energies. The extent of energies that we've seen cosmic rays go, the sun's not gonna cut it. There have been very high energy cosmic rays, and these most likely come from some of the most violent events in the universe. For instance, supernovas. When a massive star explodes, it creates a shock wave. This outgoing shock wave of expanding gas, when encountering the interstellar medium, traps ions like protons in a magnetic field that accelerates them to higher energies. These could create cosmic rays of energies up to 10 to the 17 electron volts. For reference, the biggest particle accelerators on the planet reach energies of 10 to the 13 electron volts. So orders of magnitude behind what cosmic rays coming from supernovas create when they strike our atmosphere. There is this theoretical cutoff for the energy of a bare proton coming from cosmic rays. It's known as the GZK limit. It's roughly 50 electron volts or 5 times 10 to 19 electron volts. It's not a hard and fast rule. The way it works is because these are ionized particles and space is filled with this background electromagnetic radiation that's everywhere, the interaction between those kind of lowers the energy of the particle, creating a kind of cutoff. It's not a hard and fast rule, it's probabilistic. The thing is, we've observed cosmic rays far exceed this threshold. The keyword here is far. In 1991, we saw what's dubbed the oh my god particle, and rightly so because this cosmic ray had an energy of 320 electron volt. So far more than the ZZK limit of bare protons. The most likely explanation is that it probably wasn't a bare proton, rather it could be a bare nuclei of another heavier element. A bigger concern is that it wasn't a one-off event. We've seen some more cosmic rays reach very high energies. It could all just be heavier elements, and that does solve the problem, but are there really that many heavier elements statistically? Because if not, then relativity and particle physics, which is how the ZZK limit was calculated, could come under greater scrutiny. Though right now there's no issue as such, everything is roughly acceptable. Our planet protects us from these cosmic rays. We have an atmosphere that blocks a lot of these high energy particles and shatters them to smaller energy, less lethal ones by the time they reach the surface. Our planet has this magnetic field that deflects a lot of these ions away, protecting us against this high energy radiation. So there's literally nothing to worry about on the grounds. But what about higher altitudes? We know that there's more radiation there. Recall the balloon experiment. But how bad is the situation really? Let's use numbers. On the grounds, we encounter roughly 330 microsieverts of cosmic ray radiation annually, while a single transcontinental flight could expose you to 60 to 100 microsieverts of radiation. In context, this is roughly equivalent to getting a single X-ray scan. Not something that I would call dangerous. But what about astronauts? Well, they technically are under a much higher radiation exposure. 6 months on ISS exposes you to roughly 100 millisieverts of radiation, which is roughly equivalent to getting 1,000 X-ray scans. Blimey. So obviously this puts them into a much higher risk of developing cancer or other secondary conditions like degenerative diseases. Hence, managing radiation to astronauts is one of those crucial factors for any manned mission. This year, we're going back to the moon. We have aspirations of colonizing Mars. Managing radiation exposure would be crucial for these aspirations. Computers too are vulnerable to these cosmic rays. Every satellite, spacecraft, or even space telescopes get affected by these high energy particles. There's something called single event upsets that flip one of the ones or zeros when a cosmic ray or any other high energy particle hits a node in the transistor. This could lead to a system restart or data corruption. Telescopes can momentarily be blinded by flashes of these cosmic rays, or in general degradation of the machinery. Solar panels lose their efficiency when exposed to cosmic rays. Now imagine a mission to interstellar space. Continuous exposure to these high energy cosmic rays, where even the tiniest of changes could lead to terrible consequences. Anyways, these are humanly problems that I'm sure we'll do something about. But more importantly, cosmic rays are a reminder that the universe isn't exactly for beginners. I mean, yes, it is quite for most part, but then every once in a while you encounter some of the most deadliest events. Neutron star merger, quasars, supernovas. But then these extremes are the kind of things that we need to understand how the universe plays out at higher energies, to understand the behavior of the cosmos at higher energy scales. Cosmic rays are a reminder to everything that's been happening out there. Fun fact, you can help detect cosmic rays with your phone. There's a software. Thanks for watching.